Hello, my name is David McNeill, and this is the conference paper Learning Word Groundings from Humans, facilitated by Robot Emotional Displays. This paper was completed with the assistance of my advisor, Casey Kennington, as part of our research for his Speech, Language, and Interactive Machines group within Boise State's Computer Science Department. According to Charles Fillmore's Pragmatics in the Description of Discourse, humans first learn language by engaging in spoken dialogue with other humans. If we want to model this natural language acquisition behavior using a robot, we must confront the obvious paradox. Who talks first, and how do they make themselves understood? For this paper, we test the hypothesis that emotional displays are a viable solution to this cold start problem. That is, if a robot needs to communicate with a human but doesn't have any experience with language, emotional displays are an appropriate method for communicating the robot state to its human dialogue partner. We tested this hypothesis in a live interactive study in which 21 participants were tasked with teaching our robot different words by using visual references in two back-to-back trials, one in which the robot used emotional displays and a second in which the robot did not. What words the participants taught and what objects they used as references was left entirely up to them. In addition, the robot was programmed to operate autonomously without the direct control of the researcher, who was only present as an observer in case the participant needed limited coaching or any part of the system broke. To mitigate learning effects between the first and second trial, the order in which the robot used emotional displays was alternated. Let's step backwards for a moment to interrogate our hypothesis. Why use emotional displays at all? Emotional displays are a viable solution to an initial lack of language information because emotional displays can relate the robot state to its human teacher. And emotional displays are developmentally appropriate for the most common language acquisition setting, an adult teaching a child, and would not lead a human user to make incorrect assumptions regarding the robot's comprehension. For the purposes of this study, we restricted Cosmo's emotional displays to only include those with which a previous group study of participants had determined most clearly communicated understanding or confusion. We drew inspiration for our language learning system from various sources. We've already addressed our choice of setting, but for the robot's grounded semantic model, we rely on the words as classifiers model, which can accurately classify words after only a few visual examples. This would work for a limited interaction, such as the one in this study. We use the Anki Cosmo robot according to prior work done by our SLIM research group that showed users treat Cosmo like it is the right age for a language learning task, and also found the robot engaging, all characteristics necessary if we want to enlist casual users as language teachers. That left several questions regarding how the robot was to interact with its world and with users themselves. How could the robot indicate to the user what it was looking at? And how should the robot behave outside of emotional displays to indicate to a user that it required more information from them, either in the form of more words or yes-no feedback to its own word proposals? To address these questions, we programmed Cosmo to alternate between object and user-oriented behavior, either gesturing with its wheels and lift to the object it was capturing, or creating eye contact with the user by locating their face. Interspersed with these two behaviors were constant, small, randomized movements that would demonstrate to the user that the robot was still active while its language models were training, or it was running images from its camera through its object detection module, which was the bottleneck for our system. The system we engineered for the study is outlined here according to its various modules on the left and the separate goals those modules were trying to achieve on the right. The modules are arranged hierarchically. That is to say, some tasks can only be addressed after previous modules have already completed their own goal. For example, in order for Cosmo to ground a word, it must first locate objects and navigate toward them. To do this, the visual perception module first handles the event of a new image being captured by Cosmo's camera. It passes this image to the object detection module, where a pre-trained graph taken from the TensorFlow library outputs bounding boxes around the objects. We take the bounding box that has the greatest probability of containing an object, as the learner's attention is assumed to only be focused on one object at a time. We crop the image according to the bounding box dimensions and submit this as input to a Keras implementation of an image classification neural network, trained on ImageNet corpus weights. The second to last layer of this trained network becomes the feature representation of the object, which will be used to train the classifiers of the grounded semantics module later on. First, before that, the automatic speech recognition module parses transcribed user speech, classifying detected speech into either words heard from the user, positive feedback affirming the robot's most recent action, or negative feedback doing the opposite. Those heard words will be taken and used as labels for the grounded semantics module. These labels, combined with the object features from earlier on, are used to train separate classifiers for each word, using those images that are deemed relevant for that word. Words are assumed to refer to an object if it is heard less than 10 seconds after the object was seen. This time period was chosen after a period of trial and error spent testing the robot with real users and considering the lag introduced to its interaction by the ASR, object detection, and feature extraction models. The largest square area outside of the bounding box in the image is used as a negative example to train that word's classifier. This design, in which each word acts as its own classifier, trained on positive and negative visual examples, is known as the, quote, words as classifiers design, or WAC. It looks something like this. The graphs in the center column represent every word that Cosmo has heard and has trained a classifier for, after processing at least 3 images of an object within a 10-second window after the participant has said that word. Once Cosmo possesses a trained classifier for a word, that robot will use the classifier among all the trained classifiers in its vocabulary to determine which word best fits a new object. This best fit word, which in the case of this graphic is the word yellow, will be proposed by the robot to the participant to describe that object. At this time, positive and negative feedback from the participant will be interpreted as a command to either destroy the classifier for the proposed word and start again from scratch, if the feedback is negative, or to add this new feature data to the proposed word's classifier, if the feedback is positive. In order to engage the participant into supplying these word labels and feedbacks to the robot's word proposals, the robot follows a rule-based pattern for shifting its attention between the world and the user's face, indicating through various small randomized gestures that it has either seen an object, is looking for an object, or is looking for their face. In those trials when the robot can perform emotional displays, those displays occur after the robot has proposed a word and it has received feedback from the user. We evaluate the robot's performance in the task based on the number of words it hears from the participant, the total instances of positive feedback it hears, and the total instances of negative feedback it hears. The more total words and total feedbacks, the better, as this indicates the user is more engaged and supplying more and more accurate information by which to train Cosmo's grounded semantic classifiers. We also evaluate the robot based on survey responses written by the study participants following both of their trials in the study. These task-specific questions are prepended to the standard Godspeed questionnaire. This chart shows the mean number of inputs given to the robot along with the standard deviation and the relative influence of learning effects from the first trial to the second for the study participants. Between the first and second trial, the lower standard deviation is bolded and the higher mean value is bolded. The number of positive feedbacks increased significantly from the first trial to the second, perhaps affected by user engagement with the Cosmo robot, which surveys showed increased slightly over time, along with general positive measures of the robot. The wide variation in the number of inputs provided to the robot between participants perhaps indicates the relative unintuitiveness of this robot language learning system for a human user who has been given very limited instructions on how to teach it. This chart shows the same measures, but influenced by the presence of emotional displays rather than trial order. The number of words said aloud by the human user and detected by the robot's ASR increased with the presence of emotional displays, along with the number of positive feedbacks. However, taking into consideration the significant amount of variation between users, a wider study would need to be done to validate these increases. This chart shows the correlations between participants' survey responses and those trials in which the robot performed emotional displays. Interestingly, there were correlations to robot emotional displays and participants' estimations of elegant movement, as well as the robot they deemed to be nice and interesting to work with. The higher p-values, however, indicate a need for further trials to corroborate that these correlations were related to the presence of emotional displays and not simply the design of the Cosmo robot itself. Looking at the user surveys, we find that trial order has a limited effect on participants' engagement in the task. Interestingly, participants were slightly more engaged by the second trial, perhaps after becoming more accustomed to the task setting and the robot system. The presence of emotional displays likewise has a slight effect on participants' engagement. The drift of participants' ratings to either extreme is interesting, as it may indicate that the presence of robot emotional displays is confirming participants' views of themselves in the teacher role, leading to increased engagement from those participants who believe they are successful and decreased engagement from participants who do not. In looking at participant perceptions of the robot's intelligence, we find that trial order did not have a significant effect. Participants' ratings skewed toward unintelligent across both trials, confirming our prior research that shows that users treat the Cosmo robot appropriately for a language learning task. However, with the addition of robot emotional displays to the language learning task, participants' perceptions of the robot's intelligence moved to a bimodal distribution, with more users saying the robot appeared either slightly intelligent or slightly unintelligent. Again, emotional displays appeared to cause a greater polarization in participant scores of intelligence, as it had with participant estimations of their own engagement. Whether this was due to participants' own pre-existing beliefs regarding their competency as teachers or as users of technology in general would need further research to determine. Robot emotional displays caused an increase in the number of inputs provided to the robot, which was positive for semantic grounding, as well as a wider variation in the number of inputs, which was worth exploring. The wider variation in inputs may be indicative of the complexity of this task for a casual human user who is being given very limited open-ended instruction, or it could indicate that emotional displays may be too ambiguous for the purposes of the language learning task, and that, rather than clarifying the robot's internal state, may only be translating a form of human attribution bias into a human-robot interaction. In order to clarify this distinction, more research remains to be done, with an increased focus on viewers' perceptions of themselves and leveraging other, less ambiguous means of making the robot's state more apparent to the human user. Thank you.